My name is Marius Dupuy. I'm the Managing Director of VIRES Simulation Technology, and I welcome you to this webinar, which is giving you hopefully an insight into our toolchain VIRES Virtual Test Drive. As said already by Nicole, we have a chance to answer your questions after the presentation, and I will be happy to follow up also via email on further questions. Okay, so I will get you through a few slides with a few videos, and hopefully you will enjoy it. Just very briefly about the company VIRES. We are a small company that is located in Germany, in Bavaria, so the southern part of Germany. We are currently 30-ish staff members, and we have another branch office also in Austria. The company has been founded in 1996 already, so we have been in the market for virtual environments for quite some time now. And our core product is what you actually see here on the screen. This is the generation of 3D environments, the animation of participants in these environments, and what's not depicted here, but what I will talk about, the perception of these different items that are in the virtual environments. Our software is called VIRES Virtual Test Drive. The abbreviation is VTD, and it's a full tool chain for the task that I have just described. Despite working on the software and developing the software, the company VIRES is also one of the partners and co-founders of standardization initiatives for the simulation environment, or for the simulation of virtual environments. The one that may be most known to you, if you have been in contact with MSc and Adams, for example, before, is OpenCRG, which is a format for describing road surfaces. VIRES also contributes in defining the standard OpenDrive, which is a standard. It's a file format for describing road networks with all the logics that are required to move and animate traffic within road networks. And the last initiative that was, and the most recent initiative that was founded like 1.5 years ago, is the so-called Open Scenario, which is basically using OpenDrive networks and describes in a neutral, so vendor or tool neutral format, the animation and the time variant behavior of participants within a simulation environment. You will see what I mean by describing these formats in this abstract way in the upcoming slides. Just for you to see what we are basically doing, I have a short introductory video. VIRES is working in the animation of this virtual environment, and so this is what you actually see here. It's a road. In this case, it's shown for a stereo application, so for stereo camera application. This already shows that we can serve various backends, and you have animation of traffic. We saw a guy with a broom at the beginning. So we can animate virtual environments also in different weather conditions. I will show you this later on. This is one way of showing the environments that we are working on. Another way, which is something we developed recently, is to show this environments using, for example, a LiDAR sensor simulation. And here you see the animation of a point cloud that is coming from a LiDAR, which is mounted on top, or on top of this vehicle that is here in the center of the video. But you will see more of this later on, and I will show you more of this functionality. VIRES itself is, as I said, it's a small partner. It's a small company, and it's a partner in two important research initiatives that are founded by either the German government, which is on the left side. This is the so-called Pegasus. You may have heard of this already. It's an initiative for the development of tools and actually it's about tool chains for the testing and validation of automated driving functions. From the partners you see in there, these are the automotive industry partners like German OEMs, German tier ones, some research institutes, and a couple of tool vendors in there. We are one of the partners, and we are contributing our virtual test drive software for developing the tools that are to be investigated within this initiative. And the use case there in Pegasus is the so-called highway pilot. On the right side, you see a European research initiative where we are one of the partners also, and it has different areas. In the automotive area, there's the use case of the highway pilot, which you see depicted here in this hill setup that is done by AVL. And there is also another use case which is called the valet parking. So we are partner in all of these initiatives, meaning that we are working virtually at the front end of the research that is currently going on here in Europe and in Germany. I want to give you an overview of our tool chain. We as VIRES, we are primarily working in the generation and animation of the virtual environment, which is shown here in the bottom area of this picture. Our customers, our users, will be working typically in the fields of automated driving, driver assistance, and active safety. So our users will typically be the developers of the systems that fulfill these named tasks. In between, which means between the environment and the functionality of the systems, there is the sensor layer. And this is basically the part where we are providing most of our services in order to customize our software for our users and in order to provide specific sensor environments, for example. An overview of what we do, and I have already mentioned the keywords, is shown in this picture here. I will not stick too long to this one, but I just want to show you that our primary concern is providing the virtual environment, which means we create the static environment with our tools, even to microscopic level, like you see here in this cobblestone pattern, or for highly complex road networks. We save this data in a 3D model, which is used for the graphics and for the sensors, and we save the data in a logical description, the so-called Open Drive again, and OpenCRG, to provide a base layer to define the dynamic behavior of participants within the networks. And the resulting format for the description of these of how these participants behave is the open scenario format, where we store our scenario information. Once this is done, once the 3D environment has been created, we go to the animation stage. We can provide traffic animation. We can provide vehicle animation, dedicated vehicles, and we can provide, of course, among other, road contact information and several other features. When the environment is running, all we have to take care of is, of course, to manage the whole operation of the tool chain, of a test, of a scenario, of running a scenario. So we have the tools for operating our software itself. We have tools for working with the test automation in connection with our colleagues from MSC. And we have a lot of means to provide co-simulation means, which says that we have interfaces to the most common environments for co-simulation, like MATLAB Simulink, ROS, or ADTF, just to name a few. When the simulation is running, you as a user will typically be doing what is depicted here in the bottom right corner. You will have a system or a model under test, and we provide, as I've shown in the previous picture, we provide sensor information, or we may provide sensor information for this system under test. And the sensor information that we provide may either be based on a simplified version, which is the typical object-based sensors. We can provide camera information, and we can go more into the physics-based sensor simulation, which I've shown in the video already with the LiDAR point cloud, and here some other pictures from a LiDAR simulation and from a camera simulation with a large number of light sources. You may wonder why VIRES is now talking at a webinar of MSC. The company VIRES has been acquired by MSC at the beginning of this year, and we identified a couple of fields where we can basically have synergies between what MSC has been providing and will be providing and what we are doing. Just for you who are familiar with the MSC toolchain, I just want to mention that or where MSC will blend into what we are doing. For the animation of the vehicle, for example, we will be using or offering as an option in the future that you may use MSC Adams or MSC Adams Realtime for the simulation. We will be working together with MSC on defining scenario libraries. For the management of the simulations, we are working currently on the link with MSC's Sim Manager software that you may know already, and we are also working together with MSC colleagues in California on the scenario management. Very important, especially if you're looking at the development of automated systems, is the following part that we are doing. We are working with the MSC colleagues in California on providing machine learning features. There will be a few slides about this later on. Basically, they are shown here by these three fields, which is that we are working together with MSC on active AI, an active AI gym, on an AI driver, and AI verification tools. Coming back to our part of the story, the environments where we are typically locating our software or where our software is being used by our users are the following. We have the typical desktop or HPC installation, which is used for software or model-in-the-loop simulation. And this is the typical environment where you will be running everything, which means the driver, the vehicle dynamics, sensors, any systems, and the traffic modules in the virtual domain. And you will usually try to run in non-real-time conditions. Non-real-time means for us that it's either faster or slower than real-time. So it depends basically on the speed of the slowest component in the whole chain, how fast the whole simulation will run. A specialization of this is if you bring the driver into the loop, which means you will be exchanging the virtual driver with the real driver with something like a mock-up or steering wheel or just a gamepad, and you will be doing like a typical driving simulation that you know from the games. This is where we go to the real-time domain due to the human being involved in this. And this is one of the environments where our software will also run. And we have a couple of installations at our customer sites for this. A yet more specialized case is the vehicle in the loop, which I mentioned just very briefly here. This means you're going in a real vehicle with a driver, and you may not notice this with a helmet-mounted display, not onto real road, but onto a closed proving ground, and then you can drive with a real vehicle in virtual environments. More interesting, maybe for you, the hardware in the loop test environment, which means that we will be feeding actual hardware with data that has been generated within our environment. So the sensor layer becomes very important, and the systems, of course, that are under test will, in this case, be the real systems, like, for example, an ACC control box. Okay. These are the environments. Our software adapts perfectly to all of these environments, either running natively on some of these environments or running in a co-simulation with these environments. I want to introduce now the workflow, how our software is being operated, or basically how you get from nothing to a full simulation environment. The software tools that we have start with tools to define the 3D scene, which means the static part. You may remember from the slide I showed previously. There are tools for defining the dynamic content, so to populate the scenario. And once this is done, we can go into the runtime stage, and then again, depending on whether you have real-time or non-real-time conditions, we will run the animation or the traffic simulation, as we call it in our domain. We will run it either faster or slower than real-time. In each simulation step of this animation, you will have something like a situation, and then you can pass on the information about all objects, cameras, etc., to the stages for the visualization, for the sensor simulation or sensor stimulation. So this means this is the perception layer there. There's a whole range of customization levels in our software. So you may provide your own modules and attach them to our software, which mainly communicates via network connections. You may write your own plugins for some of our components. The most prominent component for this would be our image generator, where you can run the sensor models. We have a couple of means that you can attach third-party frameworks, like I mentioned before, and also the means for doing test automation are there, which means our software may be completely controlled from outside using a command interface that we have developed, so that you can use our software in your existing environments without having to adapt to a certain test automation solution that would be provided by us. But it always means what I'm also trying to say is our software is in itself, it is quite complete, but it always depends on you as a user, which parts of the software you really need. And we will always be able to fill the gap that you may have identified in what you are using today, and fill it with our components without you having to change completely to something else. Okay. This slide again depicts what I've shown before. We have something like a creation stage where we create the 3D scene, the dynamic content. We have the operation stage where we animate everything, and we have the perception stage where we are consuming the data that is in the coming from the animation. And I will not talk too much about the integration stage today. That would be yet another webinar, I think. Okay, let's look into the 3D scene definition. The art of doing a 3D scene definition for the virtual environment is to make something that resembles the real world. And there's a couple of means how this can be achieved. We call it, depending on what you want to see in your simulation, we are using the terms of soft reality and hard reality. For us, hard reality means that you try to resemble something that is really there in the world out there. So this means you're using actual scans of data, of environments. You're using actual map data like OpenStreetMap or other data, videos and other data that you may have, and you try to convert this into something that you can use for the traffic in terms of a logical description of a road network or a road environment, and into something that you can use for the physics or for the sensors, where you create a 3D geometry and material descriptions. This may come, as I said, this may either resemble the 3D environment that is really out there, or depending on what you want to test, you can also go with pure virtual environments, which means you would not find a certain stretch of road that you are testing on in the real world, but you might want to execute a certain test. So we have an editor where you can create your road networks from scratch and provide an environment for specific tests. The complexity of this realization of either actual road networks or fictive road networks can be pretty high. In the top right picture here, you see that you may use actually, or you may realize things like multi-layered road networks. This is an example that is inspired by something that you will find in Shanghai. But it also shows another situation. I was talking about this valet parking use case before. And when you have valet parking, you would just put all of this into a single parking garage. And this is actually another situation that we can do. And I will show a brief video about this later on. But the message here is we can do complex networks, we can do multi-layered networks, we can do this in geospecific or generic ways. And if ever needed, you can also have a GPS reference for this, so you can match the simulation coordinates that you have for each object with something you will find in the real world. Another example is on the bottom right, which is just depicts that we can do even things like megacities. This is an example from, it looks like Beijing, but it's not really Beijing, but it's the typical layout of a ring road system that you would find in a city like Beijing. And on the left side, you see again that we can go to the microscopic levels where you will have things like cobblestone in a 5mm grid, for example. So we can get, if either from measurements or from synthetic data, the road surfaces into the simulation. This was the 3D scene, the static part. If we look at the dynamic content, it's a little bit more difficult to show it in a nice slide. I try to depict it here in this one. Actually, there's always a couple of sources where how you define the actions that have to be performed by entities within your virtual environment. As I said before, we store all of this information in the so-called open scenario format. And the question is, how do you get to this format? There's one way, of course, that you edit just scenes from with our editor, which I will show a little bit later on. So you can create, you can populate a road network with players, and you can assign actions to these players. This is one way. Another way is, which comes now more from the research projects we are working on, is to use something like rules to define scenario descriptions. Then you would have something like a generator in between, which could be a piece of software either by you or written by us. And we also find now it's called replay to simulation. We often find the situation that people have their own test logs from actual test rides and want to see this information in the simulation. And this is where we take then an analyzer, for example, which just takes all the canvas messages recorded on a vehicle and then generates from this the dynamic behavior of entities within a 3D environment. Again, here the synergy that you will see here, together with us having joined now MSC, is that we will be working together with MSC on creating scenario libraries for certain test cases. So you can expect that these open scenario files will become quite a large number of libraries to large extent. This is just a brief look on our editor, which can be used for editing populating the 3D environment with entities. It's a little bit hard to see. You will see some small bubbles here, which just provides like triggers for actions. You will see this a little bit larger circle, which just defines a traffic swarm area. So we can have just random traffic around our own vehicle. All of our players are then being controlled by random behavior here. On the left side, you see something like you can define your your traffic light control programs here with the timing. So we can not only control our own vehicles, we can also control, of course, infrastructure elements. On the bottom, you see that we can create a quite high number of vehicles in our traffic simulation, and in our virtual environment. This is an excerpt from a scenario where we were simulating a highway merge, and we were having something like 400 vehicles running in real time in this environment. The animation part, this is the part that actually consumes the open scenario description, makes reference to the OpenDrive file, and then I said before, we call it typically the traffic simulation part. This will animate the whole 3D environment. There will be a couple of instances created inside the traffic simulation, like our own, like the traffic running around in the simulation. But of course, you may feed in from whatever sources you have your own vehicle, using your own vehicle dynamics, or pointing again to a synergy with MSC, using MSC Adams or MSC Adams real-time controlled vehicles. And there may be live data being fed in, or different macroscopic traffic flow simulation entities that may be coming in. It's the traffic simulation itself. In our case, it means that we have individual vehicles. Each vehicle is being controlled by an AI driver that we have. So we have entities operating independently, but of course operating in a mode that they, per default, are being called autonomous drivers in our case. And these will take care not to crash into each other, follow the traffic rules, do a routing within the traffic network, etc. Each entity is represented by a 3D model. So this may be a vehicle, this may be something like, you see here a horse and some other people. So this may be animals, people, and vehicles, of course. Looking at the vehicles, each entity may be controlled by whatever vehicle dynamics you like. Of course, we have per default our own VTD, internal vehicle dynamics. You may use MSC Adams, Adams real-time vehicle dynamics, or of course your custom vehicle dynamics to do the calculation of the dynamic behavior of the vehicle. And for the input side, there is always a controller attached to a vehicle. This may be either your highly automated driving or ADAS function. And depending on what kind of function it is, it may control both lateral and longitudinal axis, or just one of these axes. And the other axis that is remaining may always be controlled by one of the other controllers. Typical use case for driver in the loop simulator is you have a human driver doing the lateral control, and you have an ACC or adaptive cruise control that would be doing the longitudinal control. And all of this, of course, may also be controlled with our VTD driver model. So there's quite a few of combinations how you can run the whole software. And again, you can do this per vehicle in the simulation, and you can do a couple hundred vehicles in the simulation. So you see the means of the scalability there. Just for Adams real-time, this is an animation given to me by my Adams colleagues. So Adams real-time means that you can have a highly accurate vehicle dynamics model. Adams is one of the most widely used vehicle dynamics simulation software tool suites in the industry, and it is proven to provide validated results when you compare it to the reality. Another case showing our synergies with Adams and with MSC in this case. You see one of our colleagues from MSC driving our simplified mock-up there in using Adams real-time vehicle dynamics in our VTD environment. So the synergies are not envisaged, they are already in place. Going further, no, not going back. I'm going forward to the means to visualize and to make actually a perception of what we do in the 3D environment. I will look into this here from this side. Before I told you about the traffic simulation that is based on the road network, and we have the behavior of the dynamic participants described in the open scenario. So we will get the position of each participant in the 3D environment from the traffic simulation. Again, remember your own vehicle may be may be fed in here, and so also your own vehicle will be at least channeled through this traffic simulation. From one of the previous slides, I said that the graphics or the 3D environment is represented with by the geometry and materials, so together defining the physics of the 3D environment. And once we have the situation or the position of everyone, and we know how the physics are, we can place sensors in the world. They may be at fixed locations on any number of vehicles, etc. And these sensors will then provide you with the data that will typically run into either, well, a driver model of yours or your highly automated driving functions. The perception is split, as I've shown before, is split in the visualization and the sensor simulation and stimulation. For the visualization part, this is, well, it's not visualization itself. It's a camera sensor. So I could have put it into the sensor itself, but usually it's well, treated a little bit different. The visualization can be done using a renderer or a ray tracer in our cases. So we can use both. We can have any optical distortion that you need. In the top picture here, you see a 360-degree view. We can have any season at any time, of course, so which is the advantage of testing in the virtual domain. We can do these fisheye effects. We can have other environmental effects like oncoming daylight, etc. So there's quite a couple of things that can be done in the image generator. We can provide the images from the image generator either in the classic way by putting them on a monitor, and you can look at it as a human or using a camera, or, which is more sophisticated, of course, even especially if you look into the hardware-in-the-loop test benches, we will provide you the images directly from the shared memory of our image generator, and you can then tweak them or do a tone mapping or whatever, and then either feed them into your system under test or wherever you want to store these images. So there's a couple of means how you can generate and consume the images. Again, this would be a separate webinar showing all of these features. This is just another example of what our image generator is also being used for. It's currently being used in quite a couple of installations for headlight simulation, high quality headlight simulation, like resembling matrix beams and other sophisticated headlight systems. So this is one more way to use the image generator. The typical way would be this one. You would be looking into a 3D environment from whatever perspective. Yet another picture just to show that we are not only working in the automotive, but also in the railroad business. In the bottom picture, you see a highway scenario with a large number of vehicles. And that's basically the camera side. Now we go into the sensor simulation and stimulation side of the tool chain. Whether it's sensor simulation or stimulation always depends a little bit on what your ADAS or highly automated driving system looks like. If, for example, we are feeding camera data or image data into a hardware camera, then it's a sensor stimulation. If we just provide data for an image processor in software, then it's more like sensor simulation. But it's in between always somewhere. The sensor simulation in our part or in our software can be done in various quality levels. The basic level that you may all know is you can use object information, like shown here in the top picture. You will use objects that are within perfect sensor cones, and you will report back the positions of all of these objects. And you can have a couple of sensor cones around your own vehicle or around other vehicles, which will just provide you with object list-based information. That's a good means just to feed a function with object lists and just to see how a function reacts. But more and more people want to look into the actual sensor functionality and how a sensor sees the world. And this is shown here in the bottom picture. We have a quite sophisticated solution using a ray tracer for different wavelengths. This one here shows the LiDAR range. And you see the difference, for example, when this LiDAR looks onto that's a bus station. And if it looks on the left side at this bus station in dry conditions or on the right side in wet road conditions. So having atmospheric effects in the and weather effects in the simulation of the sensors is one of our key areas of development currently. On the right side, you see again, like it's a snapshot from the previous video. You just see that we can also provide LiDAR information in typical point cloud format. Yet another way to use the software, if you're looking at the sensors, is of course if you are looking or if you're developing your own image processing algorithms, like what you see here on the right side. The good thing is if we do the simulation in the virtual domain, of course we all know where all objects are, so we can provide you with semantically annotated or segmented pictures, so you have like a ground truth for your image processing, and you can also have information like bounding boxes, etc. And the left side again shows that, of course, we can provide more or less consistent information. I say less because these two pictures here on the left side, they are not from the same simulation run, and you see on the bottom there is the segue, for example, missing. But this shows you that we can run also concurrently different sensor models and provide you with concurrent and consistent information at the same time for your simulation environment. A couple more slides about what we are doing in terms of the synergy with our colleagues in MSc in California. So you've seen all the information, all the stuff that we can do with our software, with the virtual test drive. We can generate the sensor information, etc. And now the question is, what's an application for this? And of course, classically, our users have done all of these applications, but we are now in the very good position that we have colleagues who are also working on some very interesting applications for the virtual testing, which are in this case for machine learning, for the highly automated driving. And so this gives us just enough leverage to develop our software together with our colleagues and make it ready to fit the needs of our prospective users in these fields. This is a little bit just an introduction of the background, why our colleagues and we, of course, are now working in this area. So the justification for doing virtual testing, that should be clear, but this picture shows it again, that you have to run a couple billion miles just to get enough confidence in your system. So the thing is, humans are good drivers, but automated vehicles must be better, otherwise they will not be accepted. And there's a high requirement for very low probability of having a fatal incident. Together with our colleagues, we now are working on these various fields that I've shown you before. There is like fields for the scenario creation. So this shows, like I've talked before about this open scenario. So together with our colleagues, we are working on creating scenario templates and populating these scenario templates and instantiating them according to the requirements that are being brought up by different authorities. If we look into the machine learning itself, we are developing currently an AI gym, which means we are training an AI algorithm based on virtual data. And of course, the reasoning will be done then using actual test data. So the whole tool chain from training a driver, verifying this driver using the AI technology and the machine learning technology, and making sure that it will ultimately also work in the real world. This is one of the key research fields that we are currently working on together with our colleagues. And we as VIRES, we are providing the virtual environment for creating this large number of test data that is required for training driver models, for example, AI driver models. Again, all these environments will count later on. It means that there will be data coming from road tests, there will be data coming from track tests, and the largest number of data will be coming from the scenarios. But of course, whatever however you trained the driver or your AI model, it has to work in all of these scenarios later on, and this is part of also the verification studies that are being done. This video here shows you one more example. It's a test case, and the question is, how are the roles between MSC, which means our colleagues in California, VIRES, and the customer distributed? So usually the customer would have an interest in, well, would first define the case, the test case that has to be done, like self-parking, like in this example here in the video, and will of course train his driver or even adapt a driver model that is being done by our colleagues in California. The metrics will typically be done by our colleagues in California. The environment, that is what VIRES will be doing. So we will be defining the 3D environment, and together with our colleagues in California, we will be defining the scenario templates and let's say the space of scenarios that has to be covered for proper testing and making sure that you achieve the reliability of the system under development that you were aiming for. With this application that I've shown, it's just a very, very small extract of what we are all working on currently. But this application that I've shown, I want to conclude my webinar